Hey everyone, I hope you're doing well. Today we will start off with a bit of a teaser. Just a reminder, the homework 1 is due tonight. There won't be a homework this week. The next assignment will be next week over Chapter 7 and possibly Chapter 8 if we get through it by next Tuesday's lecture. But again, no homework today. Okay, so this is an interview question. It was a programming question that I was asked during my second job interview. I thought it would be good to go over right now since we're building up to discussing algorithmic runtimes. So the question is given an array of numbers. Here's an example, but this is obviously not the exhaustive list of all possible arrays of numbers, and a value, a test value. Write a function that will accept both of these parameters and return true if there are two numbers in this array that when added up together equal this value. So if you run through it right now and take a moment to figure out whether or not it's true for these specific examples, you'll see that it is not. And in your mind you can kind of understand, well, I want to take a look and see whether or not it's there, and you would get up to 11 plus 5, 16 isn't big enough, 11 plus 17, 28 is too large, and 17 plus 5 is 22, 17 plus 2 is 19, that's too small, and 23 plus 1 is 24, so 23 is too small. 23 plus 2 is 25, and then anything else larger than that, just won't work. But even though this example, and they will do this during interviews to throw you off, even though this example has an ascending list of numbers, the problem, as stated, didn't guarantee that the array would be sorted. So our intuition for how to test whether or not it's true given the example is not necessarily a good solution to the problem. So the most efficient, or pardon, not the most efficient, the easiest to implement method for this is to just add up every pair of numbers. So add 1 to every number other than 1, or every number other than this 0th item of the array, to see whether or not it adds up to this test value. And if you find a match, return true, and if you've exhausted the entire list, then return false. So let me show you what that implementation looks like real quick. And then I will show you on the computer, and then I'll leave it be. If you want to solve this yourself or you want to attempt it, then whenever I switch to the computer screen, feel free to pause and come back whenever you've either got your solution or not. So let's hop over, we'll solve it, and then next week I'll show you the solution to the extension of this problem that I'm about to give you. Okay, so we have our trusty JavaScript console here. So the first thing we need to do is create an array. So it doesn't even have to be the exact same array that I'd shown you. We just need to initialize it to something. So I happen to remember this pattern because I was skipping every other prime number. With 3 being the first number skipped. Right? And then our test value was 26. So what they're looking for whenever they ask you this, and typically they'll have you write out your solution on the whiteboard, and I would have done that, except that I'm a little bit faster on a machine programming from a keyboard than I am on a whiteboard. And also, I just want to make sure that the microphone is able to pick me up as I'm typing out the solution. But what they're looking for is your understanding of how to write a function, how to declare it, and the fact that you're not relying on Googling things every minute for every possible task. Now, don't get me wrong, search engines are a necessary part of our job. I would argue that I am virtually unemployable if you remove me from the internet. There are some problems that I've worked on often enough that I could make my way through, and my familiarity with certain languages is pretty good. But as a rule, as soon as I encounter something that is new, the fastest way to find a solution is no longer to check the programming language's manual and rifle around through there and fiddle with it. Typically, if some unexpected scenario arises and you're not able to figure it out from the stack trace, then you would Google it and go to Stack Exchange or Stack Overflow to get your answers. So this is a different context. Stack Overflow is a site where programmers and developers and DBAs and so forth are able to interact with one another and ask each other questions and get answers in a common forum. Okay, so without looking this up, right? How do we solve this? So we need a function. So there are multiple ways to declare a function in JavaScript. That is another thing that I wanted to emphasize. So if you go into a job interview once you graduate, it is very possible that you will be asked to write some code. Most people are going to want to see that if they're hiring you for a position, for a developer position, that you are able to program. And if they're hiring you as a database administrator, in a junior or mid-level role, then it's going to be the same thing. They're going to ask you to write some queries and so forth. And if they're asking you, if they're hiring you for a mid-level or senior position as a developer, then you can expect that you'll also get some database questions. And so it's always to your benefit to be as well-rounded as possible. It never hurts you to know more as opposed to less. But to start out, you're going to need to carve out a strength in some area. And so I am enthusiastically imploring you all to learn JavaScript, and I will teach you a bit here and there as we go through the semester. But whether it's JavaScript or Java or C# or C or C++, you need a language that you know well enough to go into a job interview and write your code on a whiteboard instead of on a computer, because that is a very real world scenario that you will encounter. So they'll typically let you pick your language, but you need to identify what it is that you are going to be really strong at going forward. And so I recommend JavaScript because there's always an interpreter available to you, as I've said a few times now. So that's my recommendation. But when I went into it, my strength was C++. I got hired for a job writing C# code, and ever since then, C# has been my strongest language. So JavaScript is just something that I'm trying to improve at every day because I've learned to recognize its value as a programming language. So, okay, let's go forth. So I'm going to declare this function as a variable, and so I could call it has some. Right? I don't even need to declare it to initialize it. I can just declare the variable and leave it undefined for now. But now, as a variable, I'm going to assign it a function. And so functions can be created with the function keyword, and then you give the parameter list. So test array and test value. And these variables, they are stack variables. So you'll pass in a value, but the variable name will be local to the function. And So we can do it in this format, and this is the traditional JavaScript format. But I'm also going to emphasize using the latest and greatest for you all, because the new syntax, ES6, ECMA script version 6, is what's popular right now. And it's because it's just easier to read. It's less assaulting on the eyes, and so most of the jobs that are hiring for front-end developers are looking for people familiar with that skill. So learn the new skill, be familiar with the old a little bit if they test you on it, but I would focus on the styles that are more modern. And as long as you understand what you're doing, then they'll be satisfied with either way. So I'll tell you that this is almost equivalent to this, and the difference is this, right? This is a keyword in JavaScript, in Java, in C# and C++, not in C. But the scope of the variable, the keyword this, is the difference between the function declaration, where you have the keyword function, and this lambda expression, arrow function, however you want to refer to it. However, this has become quite popular, and if you're not using functions as a class or as an instance, then they are equivalent. So as long as you're not referencing a this keyword, then either format is equivalent. So okay, so now we need a default return type. So we're going to say that if we haven't found the sum, then we return false. Okay. So if we don't know what we're doing and we just needed to do something, then it's a 50-50 proposition that if we always return one way or another and they don't check our code, that we will get it right. However, they're likely to run it multiple times, checking that we will correctly return true and false. So array, and then test val, and we get false. Okay, that's great. Now, what if we tried testing for 3? That's 1 plus 2. Our function needs to be redefined. Okay, so let's hack some more. So now we need a variable. So we could use var here, but again, using the latest and greatest syntax, the ES6 extended the possibilities for variable declaration from using var to create a variable, to define a variable, to let, which is a scoped version, scoped variable. It doesn't hoist up the variables the way that var does, and const, but you can't assign to const, and since we're going to be using this in a loop and we're going to continue to reassign our iterator variable, then we're limited to let or var, so allow us to use let. Initialize it to 0, then this goes up to so it terminates whenever it is greater than or equal to the length of test array. And we increment that on every pass. And then one of the points that I would ask you or encourage you to do is ask questions whenever you're given a vague assignment like this as a programming task. So I didn't indicate whether or not it was possible to add the same number to itself. So you would ask that in the interview and say, okay, am I allowed to add the number 1 to itself or the number 2 to itself, or does it have to be distinct elements in the array? And if they tell you that it's distinct elements, then you start your inner loop at I plus 1, and again it terminates whenever it has gone beyond the bounds of the array. So now, if the value at index I plus the value here, for readability, we're going to create another variable here. So current sum is equal to the value at index I plus the value at index j. And if our current sum is equal to our test value, return true. And that's all we need to do within the loops. So what this will do is it'll start at this first element for the outer value, and then it'll test against the next item in the array, and it'll see whether or not 1 plus every other item in the array is equal to the test value. And if it is, then we're done. It has that sum. Otherwise, it'll increment this outer loop to the next number, and then it'll again test every item to the right of that, and so forth. And we need not test 1 because on the first pass we tested 1 plus 2. So we don't need to test 2 plus 1. Right? The addition has the property of commutativity, addition of the integers and the real numbers and the complex numbers. Things that are not matrices and whatever comes off of after octonions or something like that. Anyway, but these, so we've already tested 1 plus 2. We don't need to test 2 plus 1. So it's in that fashion, it's sufficient to always just test the other numbers to the right of it. So okay, we have that. So now we have our two tests from before. We have our array and test val. So we know that 26 is not in there. Then the next thing we tested was 3, and hey, look, it's returning correctly. So the next thing that they'll ask you is, well, do you know the runtime of this function? And right now, given that we haven't gone over that, and that is this is me motivating the material for today is so that you could get a job, basically, is that this is n squared. And the reason that it's n squared is even with this if condition and the fact that we're kind of short-circuiting, we're not retesting each value for every item in the array, so it's not n times n. It's close enough. The runtime of the function grows on that order. It grows in proportion to n squared because that is the principal part of the function, if you want to use those terms. And so, but basically it's the largest degreed term in the function. And so for that reason we say that it's big O of 2, or of n squared. So something of that syntax, or since we're in JavaScript, something of that syntax, right? Where it grows on the order of n squared. So what does that mean, and how do you tell? Well, essentially, if the input value, right, if you're iterating, if you have a for loop or a while loop or whatever, and you're executing it once for every item in the array, then it grows on the order of n. If you're executing it that same length, right, you're executing for every item within the array, even if you're short-circuiting it like this, then it's squared. You're doing it n times, and then within it you're doing it another n times, so that it's n times n. If you were to have another embedded loop and you were iterating over the same array, then it would be n cubed, and so forth. And just for your edification, Um, if you can run something in constant time, that's excellent. Typically, you'll take a memory hit for that. If you can run something in linear time, that's all right. Constant or logarithmic time is better. If you're performing some action, if you're changing something, then ideally you would be able to do it in logarithmic time. But failing that, something like sorting, which is what we're going to go over today, then the best you can do is n times log n. So it's a little worse than linear. It's called superlinear, but it's way better than n squared. Right? So bubble sort will have a runtime of n squared, and merge sort, which we're about to go over, will have n times log n. So for this question, you can solve it in n squared time naively, like pretty trivially. Now, the question that I have for you, and the one that will get you the job or get you your resume stuck in the maybe pile, is can you rewrite this function in a way that returns true or false correctly, so that solves the problem in linear time, so with just one for loop? Okay. So the hint that I'll give you is that yes, it can be done, and to do it, you will need to use one of the data structures that we've already reviewed in this class. So, okay, so think about that, for next time or whatever. Imagine that you didn't have the answer, but you're going to go home and study and get the answer, and the next time you interview, you'll get it right. I'll give you the answer on Thursday. Okay. Okay. So now the recursive merge sort. So we haven't really discussed sorting at all, but if I recall correctly, then in your programming classes, either in the first programming one or the second, you would have gone over sorting algorithms, and presumably you would have learned bubble sort. I don't know whether or not you would have learned merge sort, but if not, it is an improvement on top of bubble sort. And so there is a question of whether or not it's possible to get a faster sorting algorithm than merge sort. So the answer is under certain conditions, yes, but in general, no. So you can have sufficiently bad input that so everything as we attempt to optimize, there's always trade-offs. Sometimes you can get better performance by taking a bigger hit in terms of the memory that you're consuming. Sometimes you can use certain cheats or heuristics that will allow you to get better performance, but will but only under certain conditions, and if the input is sufficiently bad, then it devolves to something on the order of n squared. So I think quicksort is of that fashion. I think quicksort can be nearly linear time or something like that. I can't remember, like in the best case. But in the worst case, it devolves down to n squared. I need to check that. It might be that it falls back to n log n or whatever. But the solution, the worst case analysis for it, is what does the runtime take in the worst case? And then the other questions are, well, what is it likely to take, right? What is the average time that it might take for some statistical variance of inputs and so forth, and what's the best that it can do? Like, how bad am I guaranteeing my performance? And so if it is possible to make your code arbitrarily bad. So you could just in our example that we just went over, it's possible to just write loop inside of loop inside of loop over the test array, and then just add 1 plus 2 in that innermost layer and do that over and over again. And your program will scale, however, in proportion to the however many loops you have, and then it'll do its sorting thing or whatever else. So you can make it arbitrarily bad. There is no upper bound for how bad you can make your code, but in general, there are limitations to how good you can make it under certain cases, and so that's really what we're striving to do. And so, but things like sorting and other things, we will look to try and get something that's either linear or in log n. And we use sorting because it's something that is easy to understand. We all can understand the problem of sticking a bunch of numbers in a particular order, and it really drives home the example. So it's really easy to generate a collection of random numbers and then to measure how long it takes as you go from 1,000 elements to 1,000,000 elements, and really see the difference in performance between the different algorithms. And so, okay, but merge sort is of near optimal speed. Essentially, it's as fast as you can be guaranteed to be in the sorting problem. And whenever we take our second pass at this, I will prove it to you rigorously. We will take a look at how we know that it is the fastest runtime for a sorting problem. But for now, let's just try to understand what's going on with it, and then in the next pass we'll go into a little deeper. So this implementation is in Java, and you can see that there's 3 functions. So the main function just sets up the problem. It creates the array, as we've done before. It spits out, it prints out to the console what items are in the array, and then it calls the merge sort function, and then it spits out the sorted items. So we can see the items unsorted, and then a minute later or hopefully less than a minute later, we'll see these items sorted, and then we see the program's completed. Right? So of the actual worker functions, there are 2. There's the merge operation, and there's the merge sort method. So merge sort is the you can think of merge as a private method, kind of, to merge sort. So while we could call either, this one doesn't really mean anything to any calling function. So if we were to put this stuff in its own class, then this would be the only publicly exposed method, and then this would just be kind of a helper function. And so what we're doing is it is an example of divide and conquer for the sorting problem. So we take an array, and we'll use examples of powers of 2 for now. So if we have an array of 32 items, or let's say 16 items, then we would break it down into 2 arrays of 8, and then we would look at, and then we would handle them separately. So we look at that first array of 8, and we would break that down into 2 arrays of 4, and then we would handle them separately. We would look at that first array of 4, and we would split it up into 2 arrays of 2, and then we would handle them separately. And now that we have it into arrays of 2, we have an elementary operation that defines our sorting. So we use the less than operator to test whether or not the 2 values are sorted. So if the left value, so if A is less than B, then, and we're sorting in ascending order, then the value is sorted. Right? And if we're sorting in descending order, then the test is A greater than B. And so for already implemented sort methods, like they're essentially any modern programming language is going to provide you with a prepackaged sort function, or really a collection of them possibly that you can choose from, but at least one implementation. And you provide both the array and the test function. And so the test function will indicate, by convention, it's going to be an integer. And if it's negative, then the items are correctly sorted. If it's 0, the items are equal. And if it's greater than, the items need to be swapped in order to satisfy it. And so in the case of ascending order, you're testing essentially if you're sorting numbers, it's a minus b. And so if it's less than 0, then a was less than b, right? And you can work that out. But anyway, since we are implementing this ourselves, then we're testing for actual the single the two items. We're testing those two, right? And so you can see that the actual test occurs right here. It's within merge. So as I've described it, it's still not exactly correct, right? So we have an array, or we've broken it down to arrays of 2, but really we need to break it down all the way into individual arrays of 1, and then we merge these arrays. And so we're guaranteed that once the arrays are of size 1, that they are totally ordered. They are completely sorted. And it's because it's just a single item within the array. So the test happens whenever we merge it back together. So now we've broken our array of 16 recursively into 16 arrays of 1 unit, right? Of 1 item. And then we call merge for each pair, for each adjacent pair, so that we end up with 8 arrays of size 2 that are each sorted, right? And how do we get there? Well, if you imagine calling this with here, give me just a second. Okay, so let's take a look at an array of size 4. Okay, so we want this to be sorted into. We wanted to sort it ascending. It's exactly wrong. Every element needs to be moved in order for this to be corrected. But here's what merge sort does. So it takes this and it breaks it down into 2 arrays of size 2. And then it looks at them separately. And then it breaks them down into 2 arrays of size 1. And so as it's going through and doing this, it doesn't logically, this is what's happening. It's breaking it down at every level until it can get back together. But the order that it's doing it in is 1/2 at a time. So it's dealing with this left half of the array, and it continues to break it down. And then it tests is this less than this? And if it is, then whenever it merges them back together, it merges it with this item first, and then this item second. If not, then it swaps them. So the question is removed. We know that 4 is not less than 3, right? So whenever these arrays get merged, these arrays of 1 item get merged, these values are swapped in the returned array, right? And so this now replaces this, right? But in order to see it happen, we're gonna we're going to break it down over here. But you can think of it as whenever it joins, it is the return value for this input. Okay? And so this is done. Right? Now this is 3, 4. And so now it deals with the right half. Okay, and again, it splits until it gets down to the single items, to the elementary tests. And it again asks that single question. Okay, so now that I'm merging, is the next value in this item, is the next value in this array less than the next value in this array? Well, there's only one item in each array, so it's testing those one items. And it sees that it is not. So whenever it merges them, it swaps them. So we get 1, 2. Right? Okay, so now when this returns, the merge is undoing the splitting, right? So we talked about stacks before, right? So this is unraveling the stack. So we see it joined over here, but really it's going back up, right? So it's when this is input, it returns this. And it was called recursively, so it this is the output for this input. Okay, so now, because we're unrolling the stack, we are now merging this array and this array, and so it asks that next item question. It's like, okay, well, I have these two arrays. I have the one on the left and the one on the right, and so I'm going to go. I know that since I'm coming back up, since I'm doing the merge action, that now every item that I get, every array that I'm passed in is, with respect to itself, completely sorted. Now I just need to figure out how to order them so that I maintain that sorting. And so you can do it by testing each item in the arrays once, right? And so essentially what it's asking is, okay, I have a cursor here, right, on this first element, and a cursor here, right? You can think of it as an arrow pointing to the item to keeping place, right? So if you were doing this by hand, you would have like a bean or something that you would move to the current item so you don't lose track, right? And that's kind of what we're doing with these cursors. So you say, okay, it's the next item in this array less than the next item in this array. If it is, then I choose from here and I move my cursor forward. If not, then I choose from here and I move my cursor forward. Okay, so so we do that test. We see that 1 is less than that. So now we move our cursor forward because we picked from the right. And we ask that same question. Is the next item from this array less than the next item from this array? And we see that it's not, so we again pick from over here. Okay. And we move our cursor forward. But now we're outside of the array. So we've already included in our merged array every item from this right-hand array. Okay. And we know that the result is already completely sorted, and we know that all of the remaining items in this array, the one on the left, the one whose cursor is still within the bounds of the array, is completely sorted. So all we need to do is take, in order, every item from this left array to complete our merge. So 3, and we move our cursor forward. Okay, now we take 4. We move our cursor forward. Oh, and now we're outside of the array. We merged every item from both arrays, and so we return now we've returned from the original call, and we have a completely sorted array. So that's what's happening, right? It does that for any number, and so because it only does one branch at a time, right? It handles them separately, and whenever it needs the value from the right, then it goes down that path. But it goes left first, and then as it goes up each level, it deals with the right. So left, and then comes back up, it asks for the right, it merges them once it has those separate arrays, and then it goes up here, it's waiting on the right, so then it comes down here, it splits off the left, sees that it's down to a single item, so it comes back up, and then it asks the right, and does a merge operation, and so forth, right? So maybe that last explanation wasn't as clear as what we've done before with the cursors and stuff, so maybe just pay attention to that part. But now we can take a look at the code that does the exact same thing. But in Spirit, this is what's happening. It breaks it up, and then whenever it gets two arrays merged back together. So once it's down to single items, it's merged. Like just an array of one item is completely merged. So whenever you start merging them back up, you now have the additional property that you're dealing with already sorted arrays. Now you just need to put them together and maintain that order. And so you use these cursors to test the left and the right. Like, which one is next? Is it going to be the next item from the left array or the next item from the right array? And once you move outside of the bounds of the one array, well, you still have a sorted array in the one that isn't exhausted. And so you just pick in order each of those remaining items, and then that's your merged array for that level. And then you pass that on up to whoever called. And once you reach this top level, then you're done. You've completely sorted everything. And so this algorithm is essentially as fast as you can go. Now we'll talk about why that is later on, but for now, let's just see if we can understand the code associated to this logic. Okay, so merge sort goes through and it breaks it down, right? So I said we split it up into left and right. So how do we do that? We identify a midpoint, and midpoints are just dividing by 2 basically. And so we declare a left half, a left array, and a right array. So the left array, because we count 0, is one item larger than the midpoint. And the right array is going to be the size of the input array minus the size of the left array, the number of items in the left array. And so this midpoint plus 1 is exactly the size of the left array. So I could have left it like this. I could have instead declared this as left.length or size of left or left.count, whatever it is in Java, I don't remember. But it's the size of the input array minus everything that's already been claimed by the left. And so now we go through each item in the array. Oh, and we copy it over. Okay, so the reason that we're passing through this is that we've initialized the size of the arrays, but we haven't stuck anything in them. So they're going to be whatever the default values are. In Java, it means that it's going to be all zeros, and the same thing in C#. In C, it means it's going to be whatever was assigned to that address, that memory address, the last time that it was used. So it could be any possible junk there. So we initialize our variables, right? So here we're just copying it over until we reach the midpoint, and until we've exactly reached the midpoint, right? That's why this equal. And then for all of the remaining items, we assign it to midpoint plus 1 I. Oh yeah. And so this subtraction here is that we need this so that whenever we start assigning to right, we're assigning it at 0. So I at this point is midpoint plus 1. And so to get it back to 0, we have to subtract that. And then, so that the next item is 1, we continue to subtract the number of items that were stuck in this left array. And so that's what's going on here. And so on the right, we're still just copying items. It's just the next item in the array. Okay. And then it calls return here, but it's not actually returning. It's saying, well, whenever merge is done with whatever it's going to do, return whatever merge says, right? And so, I said that we were unrolling the stack that the recursive function calls. Well, that's what is happening here. So as soon as merge is done, then we're ready to go back to whoever called merge sort recursively. And so within that, so even though we have a return statement here, we're not done. We're just saying, well, whenever all this junk is done, return whatever merge spits out. But before we can call merge, we need to deal with our left branch. I said we do left and then right. And so we pass in the left, so that left half of the array. In our example with 4, then the left is now 2. Okay, and so we go through and we do the same thing, and it splits it up into 2 arrays of size 1, right? A left and a right, and then it calls them, right? And so once it's down to length 1, it just returns immediately. So nope, there's nothing. It's already sorted, right? We discussed how any array of length 1 is already sorted. So it just returns immediately. And so great, now we have both a left and a right, and we can pass them into merge. Right? So at the lowest level, this left array is of length 1, and this right array is of length 1. So now we pass it into merge. Okay, and we have all these intimidating indices here that are keeping track, but essentially what that's doing, so the I, J, and K, how I had the cursors that were going through, well, the I is the cursor for the left array, the J is the cursor for the right array, and the K is the cursor for the merged array. And so it just keeps track of where it gets put into the merged array. And so this happens, as you can see, it always happens in succession. It's always the next item, the next place in that array. And merged is equal to the size of the 2 arrays combined. So it is the gluing to the, well, it's not gluing, it's more stitching, right? The precise recombination of these 2 previously sorted arrays. And so so we keep track of our cursor on the left, and we keep track of our cursor on the right, and at every point we're asking, do we pick from the left or do we pick from the right? And if this is true, if the left is less than the right, if the next item that the cursor indicates on the left is less than the next item that the cursor indicates on the right, then take from the left. And if not, then take from the right. And so we'll continue this operation until we've either gone outside the bounds of the left array or the right array. And so this could include an if condition, if and then while inside, but it doesn't execute if it's false anyway, so the while is kind of its own if. So we don't have that, but if there are items remaining in the left array, so if the cursor has not exhausted that left array, then take from the left until it has, and then just stick it in the next spot available in the merged array. Otherwise, take from the right. But we don't have an if or else if, right, as I just explained. So just 2 while loops back to back, both testing exactly what it's looking for, is sufficient. So we're asking, are there any items in the right array? Is that cursor still pointing to some valid number in that right array, or some valid slot in that right array? If so, continue to take from it until you've exhausted every item in it. And so this deals with the case that the possibility that each array may still have something to offer, and this deals with the with the leftover case. So one array is going to be exhausted before the other, and we need to merge every item in both arrays, and so this just picks up all of the leftovers. And then once it's done, we return that merged result. So we deal with the left, and then we deal with the right. So it comes in and it deals with the right. First the arrays of length 1, and then once that returns a pair, we pass that into merge, and then that gets returned, and so on and so forth. So that's it. That's everything that we're doing in merge sort. And so if you're doing it by hand, it's really not that bad. Like, you could probably do this on a sheet of paper for an array of small size. But getting to the point where you can comfortably program such a solution, it's a little more difficult than it sounds. You may get tested over this in some of your classes, and the problem is it does seem intimidating at first, but if you work it out and you think through just the general principles that we're doing. So we're splitting it up until we get to a case where every broken down, until we've divided it so that we have some new property. So we've broken down the array from an array of n items to n arrays of one item, and now we have this new property that we're going to leverage. And the new property is that now every array in our arsenal is sorted. And so what can we do with that? Well, now we can stick the arrays side by side, left and right, and we can stick a bean or a cursor or some counter over the number that we're dealing with, or the array slot that we're dealing with. And we're going to go from left to right in each of our, or we're going to go from beginning to end in each of our two arrays, our left and our right array. And each time we take from one array and stick the value into the merged array, we're going to increment our cursor. We're going to move our bean to the next to be above the next slot in those two separate arrays. And then we're going to make sure that we've moved our bean or our cursor or whatever to include every item in both arrays, so that we don't say that we're done until we've pulled in every item from both arrays. And by doing it in this fashion, by always keeping it ordered whenever we merge them back, we go from our n arrays of completely sorted arrays, each one item in size, to doubling them in size each time with m plus n operations. So we're counting through each array once. So as we go back up, we just need one pass through each array, which isn't that bad, in order to continue to maintain that sorted property. But whenever it comes out, it's still sorted. And so I'd mentioned that there are advantages to maintaining sorted data. That property gives you something that you can leverage. You can use binary sort, or in this case, you can merge two arrays, and they don't even have to be the same size, but you can merge two arrays and get an output that is also still sorted, so long as the inputs were sorted in linear time, and that's fantastic. But because of the recursive nature of it, the fact that we're having to call it over and over again in order to split it up, that adds an additional factor of log n. But that's essentially all that we're doing. Break it down, and then whenever you stitch it back together, continue to test for whatever ordering property you want, so that we're always taking the next smallest number, the smallest remaining number from each set, whenever sorting ascending. Or if we're doing the opposite, then test for the opposite, right? But And if we do it in that fashion, then each time it returns, it is still fantastically sorted, even though the array has effectively doubled in size. And that's it. It's just those two things. Break it down, and then put it back together, but each time you put it back together, make sure you do it the right way. Make sure you follow these rules, and you'll have a sorted array. So I would encourage you to test it, right? And test by writing the implementation. And if you're familiar with Java, then create a project and test it. Type it out so that you're familiar with it. Try and switch this condition right here, and make sure, make sure that you get that the array is sorted in descending order. If you change this from less than to greater than, if you change this, so that would do it. Okay, and then that's it. Or you can test it in some other language. You can try translating it to JavaScript or whatever. Okay, so this, with each time you made a call, you created a new integer arrays each time you split the levels, and then each time you merged, you created yet another integer array. So it is possible to perform these actions without creating a new array, and so this one is recursive, but it's in place. So instead of creating a new array each time, we're reusing the same array, but just swapping the elements in place. And so it's still the same two functions. We still have merge sort, which is the divide part, and then merge, which is the conquer part, where we're stitching it back together. So if you've got the time, and hopefully initiative isn't the problem, but if you've got the time, then try it both ways. And so it's fairly straightforward to translate into another programming language. But the logic is the same. You can mess around with the input. You can try randomly generating the arrays. It's probably a little more work to do it in C, but if you're using any other language, then you can randomly generate the values. If you do it in JavaScript, then you can use another facilitated language. Then you can use a random variable generator to do it, to create however many values you want, and then spit it out and make sure that it's sorted. Okay, so now in order to answer our programming question, like how do we know that it's that our loops are n squared or n log n, or that our recursive functions or our loops or whatever are n log n? How do we know how long what we're writing is expected to take to complete its execution? And the answer is by starting with the basics of counting. So the product rule is pretty simple. If you have n1 ways to do a particular task, and then you have a second task that needs to be done, and there are n2 ways, or we could give that another variable. We could call this x and we could call this y. And there are n1 times n2 ways to do both actions in succession. So you can choose from x ways to do the first task and y ways to do the second task, and your total array of possibilities is x times y in number. So that's the product rule. Is that if you have to do two things in succession, then the number of ways that you can do both as a pair is x ways or y ways. And so Yeah, essentially, if you are if you're a gambler, then the product rule is essentially like and you parlay, right? So if it's a a gambler's delight, I guess, if where essentially you're claiming that you want to bet on two events or whatever, two games or two separate bets, and you want to combine the potential for your winnings. You want to multiply your winnings together. Then you're having to multiply your chance of failure as well. And so if you have a 50-50 way of winning that first bet and a 50-50 way of winning the second bet, and you make just two bets simultaneously, your parlay is only two events, then your chances of winning your overall bet, where you have to win all events, is your chance of success here times your chance of success here. So your 50-50 proposition is now down to 1 out of 4 instead of 1 out of 2. And it gets progressively worse. So we do try to promote software development as a career rather than gambling, and hopefully that illustrates it right there. But that's essentially the principles of the product rule. So X ways to do the first thing and Y ways to do the second, and then combined there are X times Y ways of doing it. Okay, and so they do give an example, and so there are 2 new employees at a company, and there are 12 offices. So they're the first 2 employees in the new office space, and they get to choose who they get to choose their own office, right? So they flip a coin, and Sanchez, the first person, has 12 offices to choose from because he won the toss. He gets first pick. All of the offices are empty, so he can choose from 12 different offices. Patel, the second employee, has all of the offices that Sanchez did not choose, so he has 11 choices. So combined, their office arrangement has 12 times 11 possible pairwise assignments. So combined. So it's not asking how many different or what are the how many different ways will the remaining 10 offices be situated or whatever. Like, we're actually curious about the assignments themselves. So if Sanchez is in office 103 and Patel is in office 108, then those are the actual assignments. And so that's distinct from if Patel was in 103 and Sanchez was in 108, if that makes sense, right? So we actually care about the ordering here, or the assignment themselves. So there are 12 times 11 ways to assign those offices, or 132 ways. And I make a note that we can already see the introduction of combinatorics just from the product rule, this one simple principle. And so if there were a third employee, we'll call her Claire, then she would have 10 choices, 10 open offices to choose from. And so the combined assignment of these 3 offices would now be 12 times 11 times 10. So Sanchez's choices times Patel's choices after Sanchez times Claire's choices after Sanchez and Patel results in this 1,320 permutations. Right? And later we'll call them R permutations or whatever, but it's a special condition. And so there's still offices remaining. If we were to assign all of them, then it would be n factorial ways of choosing it because of this product rule, right? So the next person would get to choose from 9, and the next person would get to choose from 8, and so forth. And it would continue. But this is directly from the product rule. And because mathematicians like succinctness, they realize, well, it's going in this progression. We're selecting without replacement, and we do care about the assignment. So a shorter way to write this would, instead of be n1 times n2 times n3, until we reach the k number that we care about, would be to write n factorial and then divide out. Just don't count these other numbers that haven't chosen. So these k or n minus k people that haven't chosen, right? So this isn't really anything. It's just the number of times that we haven't applied the product rule. So just exhaust it and then remove them. And so this is just a notational convenience, but really this is the heart of what we're after. Okay, but sure, this notational convenience will come back in not very long, right? So here k is 3, and we see that in order to get the product rule applied to 3 choices where we care about assignment, that we get n factorial over n minus k factorial, or 12 factorial over 9 factorial. Right? And so this is just notational convenience. But we can see from here that if we didn't care about assignment, right, we just wanted to know how many different arrangements of occupied offices there would be, then we wouldn't care about the 3 people that chose or the ordering of it. So we would divide out that which we don't care about. We would remove the permutationness of it, right? And so there's k factorial permutations. And so all of a sudden, right, if we only care about combinations and we no longer care about assignment or ordering, then we end up with this. We end up with our notational convenience divided by the permutations, the number of permutations, because they're all considered equal, right? It doesn't matter who chose which office, right? The 3 corner offices are gone, and that's all the CEO cares about coming in, right? And so we end up with this new notation. Well, this is n choose k, and so that's kind of how it was derived. That's where that formula comes from, and it follows essentially directly from the product rule, and you can kind of see it in that example. Okay, so the sum rule is really simple. So if there are n1 ways of doing one thing, and there are n2 ways. Sorry. Okay, so think about the example. You're given as a punishment that you have to either sweep or mop a room in a particular house. And so you can only you have to vacuum or mop. And so you can only vacuum carpeted rooms, and you can only mop hard floor rooms. Then there are n1 ways. There are n1 carpeted rooms, or x carpeted rooms, and there are n2 hard floored rooms, or y rooms that you can mop. Then in order to satisfy your punishment, right, there are n1 plus n2 ways of doing that, right? Or x plus y ways of doing that. So there's x number of rooms that you could vacuum and y number of rooms that you could mop. Okay, and so that's the sum rule. Great, we've introduced addition, so it doesn't seem all that significant. But again, from humble origins, we will build complex things. Okay, so the example here is that the university is assembling a committee, and they need from the math department either a student or a math major to represent the math department. And then how many different individuals do they have to choose from? So assuming that there's no overlap, and there's 37 faculty members and 83 majors, then it's again n1 plus n2 or x plus y or whatever, or 37 plus 83. So there's 120 possible representatives. Right? And so the sum rule is pretty straightforward. I think the product rule is pretty straightforward too. Okay, the subtraction rule is the principle of inclusion and exclusion. So if a task can be done either in one ways or in two ways, then the number of ways to do it is n1 plus n2 minus the number of ways that are in common, right? And so if we go back to this previous example, and there was a faculty member, say there was an undergraduate who was extremely advanced and became a grader for some of the lower level courses in math, and he was counted among the faculty and the mathematics majors. Then by adding them together, you would have counted this individual twice. Okay? And so the subtraction rule says, well, you have to correct for that. If there is anyone that meets both criteria, or if there is a way that these conditions are satisfied, or if there's a way that satisfies both of our methods of counting, then when we add it together, it is counted twice, and you have to reduce your total by the number of items that were counted twice. And so when it's separate, it's 37 plus 83. But if we imagine that one of these 83 gets added to the faculty, well, it's not a new individual, right? There's still only 120 people to choose from. We've just increased this to 38 by introducing an overlap between the faculty and the math majors. So in order to continue to keep the tally accurate, we can still add the numbers together, but then this becomes 38. But then we subtract by the overlap, by the individuals we've counted twice, and so that correction is the subtraction rule. And as our number of sets increase from 2 up to some arbitrary number, we see that simple subtraction of overlaps can itself become complicated, because it's possible that by applying our sum rule, we've counted an individual twice, or we've counted a task twice, or whatever it is that we're counting. And so we subtract it, but then it's also possible that we overcorrect by subtracting these intersections where multiple intersections include that same task, right? So I will go over that in a little bit when we get to the principle of inclusion and exclusion. But for two sets, it's the subtraction rule, and for arbitrary sets where we have to continue to correct, like if we've over subtracted in our efforts to correct, then we have to add values back in that we over subtracted, and then it's possible, depending on the number of sets we have, that we've again overcorrected, and you continue to make this series of corrections with increasing intersections, right? So you add all the values together, and you subtract the values that are intersected in two sets, and that potentially overcorrects. So then you add back in all of the values that are intersected in three sets, and then that again may have potentially overcorrected. So then you would subtract all of the values that were intersected in 4 sets, and then eventually this madness, this overcorrection by over subtracting and then overcorrecting by over adding and so forth. The madness ends if you continue this process up until you're correcting for the values that are intersected in all sets, and then once you've dealt with that, then your process of correction is done. But that is essentially the principle of inclusion and exclusion, is making these corrections for double counting and then overcorrection. Okay, and so the example that we give here deals with bit strings, and so you'll see me use a lot of examples with bit strings, and it's because it is it's just really really convenient to consider problems in binary. 0 and 1 defines true and false. Or false and true, I guess. It defines exclusion and inclusion in terms of membership to a set and so forth. It is how we represent words in machine language, right? Zeros and ones, and so it turns out to be a little more than trivia. And so I'll continue to try and warm you to the idea of using them. Anyway, I covered a little less ground than I wanted to. I think I spent more time on merge sort than I wanted to. But we'll pick up here next class, and then we'll go forward. And hopefully, if I'm focusing on this, then we will make it a little further in the notes. But before we go, okay, maybe I'll just release it as an additional aside video. But I will provide you with kind of an introduction to HTML for anyone that's not familiar with it. And so I want to encourage you all to use your developing skill sets as you go forward. So HTML was, I believe, created as this improvement on rich text. So in addition to providing all of the visual representations of a rich text file, it was hypertext. You could link to other documents. You could share these files in an easily transferred medium, like by viewing it through a web browser and by linking it to other files. And in particular, HTML is a document format. And so right the very first line of every HTML file, if it's properly defined, defines a document type. And so at its origins, and I'll repeat this in the video, but at its origins, the internet was defined, was kind of created as a way to share ideas and share research, with the principal benefactors being, or beneficiaries being the collegiate system, the universities, the academic researchers, so that they could share their documents. And so in this first example, I will show you kind of how the syntax lends to that, and how to just create a raw HTML file. And for the next few of these bonus lessons that I post, I'll continue to build on that, and we'll introduce CSS, and we'll kind of break up the file a little bit and show how it can be used to navigate, and just some of the raw principles of HTML. And then we'll, as we add CSS for styling, we will begin to introduce kind of raw JavaScript as well, or in order to add functionality to it, to our page. And then once we're comfortable with that, we'll begin a new example. And hopefully by the end of the semester, we're just doing some really cool stuff, and you can see how with just HTML and JavaScript and CSS, you can do some kind of remarkable things. I hope to have some good examples for you guys, ladies and gentlemen, by the end of the semester. But we'll see how it plays out. Hopefully, it appeals to at least some of you, and you're willing to put in that little extra time in order to prepare for that first job interview and life after graduation. I know it's a little early to think about it, but it is this is a discipline that you need to invest in and plan on it providing you with income, and invest your time accordingly, and in order to succeed whenever you get out there. So okay, thank you for your extra time, and I will speak to you all on Thursday.